So, we have been looking at direct proof methods. In the last class, we saw an example which I am beginning with today, which is the example given here, that given these three formulas P and Q implies R and not Q or S implies T and not T and not P, that we can derive R essentially. We had also said that any direct proof system needs to work with a set of axioms to start with, and we had said that in our case the axioms are the ones which are given to us from the domain essentially. But there is an interesting theorem which says that proving certain things based on certain premises, in this case we have three premises and one conclusion, is equivalent to proving this formula which says that you have P and Q implies R and not Q or S implies T and not T or and P. The whole thing implies R. There is a theorem in logic, a very well known theorem, it is called the deduction theorem. Which says that every time you make a deduction based on a given set of premises, it is equivalent to showing that a certain formula, which is the one that we have written in black here, which is made up of the givens and the conclusion, is a tautology. So, notice that this formula is a tautology. So, if you have any problem that you are trying to solve, in which certain premises are given to you and you want to show certain conclusions, it is equivalent. We can always find an equivalent formula which is a tautology essentially, and if you can show that this formula is a tautology, then the earlier proof holds, and this property is given to us by a theorem called the deduction theorem, which we can write as follows, that if you want to show using KB is alpha, and if KB is equal to a set of sentences, let us say A, B, C, D, then in our old notation you would have written as you are given A, you are given B, you are given C, you are given D, and you want to show alpha, which is the same as what we have written here. You can derive alpha from a knowledge base if and only if the following sentence can be derived: A and B and C and D implies alpha. And notice that when we have written this A and B and C and D implies alpha, we have not written anything on the left hand side of the derivation symbol, which means you do not need any premises to derive it, which means it is true under all valuations. So, which means it is a tautology essentially. So, in that sense, if you can find a proof system which is able to derive all tautologies, then in effect you can solve all problems, all deduction problems essentially in propositional logic essentially. And as I said, there was one of the earliest proof systems that was given to us was by the well known logician called Freges. So, I had said earlier that what logicians were trying to do is find out what is a minimal set which will allow you to prove all tautologies in propositional logic. So, what do you mean by that? That given an alphabet, let us say P, Q, R, S, T, all true sentences should be able to be derived essentially. So, such a system is called a complete system. So, there was a kind of a competition between logicians to try and devise systems which are tiny, but which are complete at the same time essentially. So, what do we mean by tiny? So, when we look at this Freges propositional logic, we will see that he gave us a logic in which there were only two symbols, which is negation and implication. So, first of all, of course, you must convince yourself, and we have gone through this argument. So, I will not go through this again, that anything you can say using other connectives can also be said using a complete set of connectives. So, what Frege showed along the way is that this pair of connectives, the negation and implication, is a complete set. For if you want to say A and B or A and B or C, everything can be said using the implication and the negation sign essentially. So, for example, a simple formula like A or B is, as you can see, equivalent to saying not A implies B. I can always express it using just the negation and the implication. And in fact, the way to show that this set is complete is to show that every other connective can be expressed using these two connectives. So, here we have shown that OR can be expressed using not and implication, and you can show for other connectives as well essentially. So, Frege's system used only these two connectives, and it used only one rule of inference, which is the modus ponens. And he showed, we are not going to go into the proof, because our interest is more in algorithms that will come by, and in any case we are not going to be interested too much in direct proofs, but he showed that his logic or his propositional calculus, as he calls it, is both sound and complete essentially. Anything that you just choose an alphabet of primitive propositions, and anything you can say using that alphabet can be can be expressed using these two connectives, negation and implication, and all tautologies can be derived essentially. So, our emphasis is on derivation essentially. So, of course, he gave us a set of axioms, which is what I need to state next. So, we are looking at Frege's propositional calculus. If you just search for this phrase on the web, you will find on Wikipedia a very nice description of Frege's calculus, along with a sort of very interesting example proofs that you can give essentially. So, I do urge you to go to Wikipedia and look for it. So, Frege's propositional calculus is made up of a set of axioms. So, remember that we had said there are two kinds of axioms. One is the logical axioms, which are tautologies, and the other is the domain specific axioms of the kind we saw in the example that we just solved in the last class. So, Frege's propositional calculation works on logical axioms, and there are 6 axioms. So, which are written as follows. So, let me write here. So, they have been given names. The first axiom is called then 1, A implies B implies A. Again, remember that A, B are propositional variables. You can plug in any large formula inside this. All you are saying is that this formula is an axiom. Whatever you can plug in for A, you can in fact plug in this formula itself for A and some other formula for B, and the whole thing will turn out to be an axiom. One way to of course verify that this is a tautology is to simply construct a truth table. Another way is to try to find a proof in some other systems. We will try and do that also later. But for the moment, let us just accept them as axioms. This says that if A implies B implies C, then if A implies B, then A implies C essentially. Sorry, then 3. And 3 more axioms which deal with negation sign, which are given the name based on Frege. So, you will see some connection with modus tollens here, how the connection between modus ponens and modus tollens. Whenever A implies B is true, not B implies not A is also true essentially. And there is only one rule of inference, which is modus ponens, which says that P and P implies Q, something implies Q. So, this is Frege's propositional calculus, 6 axioms, one rule of inference, and he showed that all tautologies of propositional logic can be derived from here essentially. So, what we will do is we will look at a couple of proofs just to get us a flavor of how this works, and then we will try to see that. So, the what to find sort of slightly more what should I say methods which can be automated more easily. So, we will see that a lot of guesswork is kind of involved here essentially. So, let us look at a couple of examples. So, we want to show this, and so this is called a derived rule. Okay. So, if you try your hand at Frege's calculus, you will see that proofs. So, in fact, in a moment we will look at a proof of a very simple statement called, which is P implies P. We will see that proofs can be actually terribly long proofs essentially, and you are not really going to be interested in long proofs. So, what logicians often do is that they have derived rules of inference, which says that once you show that another rule is sound, then you are allowed to use that as a shortcut essentially. So, we will look at one derived rule which is called as TH star TH1 star, and this rule says that if you have A implies B and if you have B implies C, then you can conclude that A implies C. So, if you look at the Frege's axioms, I have lost the pages now. Okay. If you look at this Frege's axioms, then this is all that is given to us essentially. And what we now want to do is to derive this fact essentially. So, let us see how we can do this. We start with B implies C. Where does this come from? This is a premise that is given to us. We are given two statements, and based on those two statements, the two statements are A implies B and B implies C, and now we want to show that A implies C is true. So, remember that this notation that we have left hand side of this symbol here is the antecedents of what is given to us, and the right hand side of the symbol are what we want to show to be true essentially. So, this B implies C is given to us, then we look at an example of B implies C implies A implies B implies C. Where did I get this from? The first axiom. So, this is from then 1. In fact, it is then 1, except that instead of A implies B implies A, I have written B implies C implies A implies B implies C essentially. Now, you can see that I can write A implies B implies C. How? Because of 2, 1 and modus ponens. This, as you will recognize, is then 2, the second axiom given to us by Frege, and then I apply modus ponens again. So, I get A implies B implies A implies C. So, by 3, 4 and modus ponens. Then A implies B is given to us, and therefore, we can conclude A implies C. From 6, 5 and modus ponens. So, this is a proof in Frege's propositional calculus. We have shown that. So, you can see that this basically is a rule of transitivity, or there is a corresponding rule which I had mentioned sometime, it is called hypothetical syllogism, which says that if A implies B and B implies C, then you can infer A implies C essentially. We will look at other ways of arriving at these proofs essentially a little bit later essentially. Let us look at the proof of a simple statement, which is to show that A implies A. Show that A implies A is a tautology. Now, obviously, this looks like a very trivial statement to us essentially, and we accept it to be true. We can simply construct a truth table and see that it will be true and so on. But we have thrown away the notion of using truth tables and semantics and things like that, and we are saying that we are going to rely on Frege's machinery to produce sentences for us. So, can we produce this sentence? And in fact, on the web page that I mentioned to you, the Wikipedia page, there is a nice proof which I am going to reproduce here essentially.
Sir, why can't we build machines which use truth tables for smaller formulas, and then we can use the theorems for the bigger formulas?
Which use truth tables for smaller formulas?
Yeah,
and
like if we have only 2 or 3 variables, then solving it via truth table is feasible.
Well, that is true, and in fact, we will see that some of the indirect methods that we will look at, the tableau method in fact is trying to do semantic analysis, which much later actually was recognized by people as a proof system essentially. So, it is true that, so we can try to show that a formula is unsatisfiable, and then when we fail to show that it is unsatisfiable, we will conclude that it is satisfiable and things like that essentially. But a more compelling reason for resorting to proof methods is the fact that truth tables do not carry forward to first order logic essentially. It's you just cannot construct truth tables for first order logic. So, there we need a formal system essentially. So, here is a proof for A implies A. Where does this come from? Can you see? I think. No, it is from then 2. So, if you look at A implies A here and A implies A here, this is where we substituted for B. So, and this A, the third A, so this was B and this one is C. So, we have this. When you look at it, you can see that we are trying to use modus ponens all the time. There is the only rule of inference available to us. So, once we have a large implication, we are trying to generate a formula which will match the antecedent. So, for the first implication, you can see that the second sentence is something which matches the first one and will allow us to use modus ponens. So, where did this come from? This is an example of then 1, right, where this corresponds to B again. Now, we can infer what is there on the right hand side, that is A implies A implies A implies A implies A, which is from 1, 2 and modus ponens. Already you can see that the conclusion of this statement is what we are really looking for, which is A implies A. So, if you can generate the left hand side, then we can get to the right hand side essentially. So, the left hand side is easy enough to generate. A implies A. This is just an example of then 1, where we have substituted A instead of B, and then finally from modus ponens. Right. So, what is the difficulty with this proof method? Freges showed that it is complete, but you can see that it involves a lot of guesswork. Or you might say it involves a lot of inspirations. You have to produce those particular instances. You can see that the first formula is an instance of then 2 essentially, which means that we plugged in certain values for B and C and we got this formula. So, you have to somehow produce magically that right instance. If you can do that, then of course, you can generate a proof. But even for such a small thing as this, we ended up producing a fairly long proof essentially. And you can imagine that for more complex formulas, the proofs tend to be even longer essentially. So, let us look at another variation in direct proof, in which you are allowed to use assumptions. So, very often if you make certain assumptions, so if you remember your geometry proofs, you would say okay, draw a line from here to here or something like that. So, again you have to be creative here. or you have to do some very informed guesswork to make the right assumptions. But if you can do that, then you can get to proofs fairly quickly essentially. Some people have called these as Hilbert style proofs. So, Hilbert, as you probably know, was a great mathematician who at the beginning of the last century had posed a set of 30-40 problems, which he said that if you can solve these problems, then you have solved most of the work in mathematics essentially. And unfortunately, he received a great setback because somewhere along the line Gödel came along and he showed his proved his incompleteness theorem, and he said that you can never build powerful enough systems which are complete essentially. Okay, so, basically Hilbert style proofs make certain assumptions and they allow you to come to conclusions based on those assumptions. So, the basic idea is this, that if you make an assumption alpha and you are still given the knowledge base, but you are adding certain assumptions to this, then you do some steps of derivation and somehow you produce beta. Now, you can see that this beta is dependent upon alpha. I mean, it may turn out the case that because you assume alpha to be true, you could prove beta essentially. What Hilbert style proofs do is you can. So, some people like to draw a box around the assumptions and say that you want to come out of the assumption, you must replace this with alpha implies beta. So, as it turns out, this gives us some very short proofs. We can generate some really short proofs essentially. So, to take an example, you make an assumption P and therefore, you conclude P identity essentially, and therefore, you conclude P implies P. Now, this is a derivation, this is not a, we are not looking at a truth table or something like that essentially. Or let us look at then 1. Of course, we can construct a truth table for all these things, but what does then 1 say? A implies B implies A, right. You can see that so Hilbert style proofs they work only with the implication kind of a thing. In fact, Hilbert's calculus use only the first 2 of the axioms that Frege uses, and he tries to show that you can do a lot of things with that, but of course, it is not a complete system essentially. So, let us see if we can prove then 1 here. It is not so hard. You make an assumption A, then so let me write this in a linear fashion, then you make an assumption B, so first statement is an assumption, second statement is an assumption, third statement is from 1. So, I will just write from 1 an identity, you are allowed to reproduce it again. Then the fourth statement is B implies A, in the sense that you had made an assumption B and then you showed A. So, therefore, when you write B implies A, then you can throw away the assumption B, and then the fifth statement is A implies B implies A, which is you are going back to the first one. So, you have done away with both the assumptions and you ended up with a formula, and therefore, you accept that formula to be true essentially. Let us look at a couple of more examples.
So, in higher levels of assumptions, the previous assumptions can be used as identity.
Yeah, so let us look at this example and it will make things clear, or maybe we will show then 2 as a proof for then 2. Find it. So, let us start with the highest level assumption, which is the left hand side of then 2. So, this is an assumption. Okay. So, let us put it in a box. Then we are interested in the right hand side. So, we will make another assumption, which is P implies Q. We will put it in a box which is inside this outer box. So, whatever is in the outer box we can use in the inner box essentially, as long as we are inside the outer box essentially. Then we make a third assumption, which is P. So, the third box is inside, nested inside those two boxes essentially. So, all these three assumptions, P implies Q implies R, P implies Q and P essentially. Now, we can get Q. So, let us give numbers to this 1, 2, 3, 4. So, from 3, 4 modus ponens, then we have Q implies R from 3, 1 modus ponens, and then we have R from 4, 5 modus ponens. Okay. Now, if we close this innermost box, that means we have thrown away the assumption P essentially. So, we can write P implies R. Okay. Then we close the second box. So, we have thrown out the assumption P implies Q. So, we can write P implies Q implies P implies R. And finally, we close the outermost box. So, we have then 2 . We made 3 assumptions, then we close all the 3 assumptions and we ended up with this formula, which is actually then 2 essentially. So, Hilbert's side proofs tend to give us shorter proofs essentially, but again there is guesswork involved, which is not so easy to implement in programs essentially. I mean, you cannot have a program making an inspired guess or something like that. So, for this reason we find that direct proofs are hard to implement. So, when we move to first order logic, we will still look at some examples of direct proofs which are used in real life. So, forward chaining and backward chaining for example, but we also want to look at other proofs which are easier to implement in algorithms. So, in the next class we will look at our first indirect proof method, which is called the tableau method essentially. So, we will stop here. Actually, the time has been over for some time. So, we will take a short break, let us say 5 to 10 minutes, and then we will assemble.